So you remember when we learned about rate laws in previous video, I told you that the order of each reactant, the exponents, had to be determined experimentally. You can't just look at an equation and figure out the form of the rate law. You actually need some experimental data. So that's what we're going to learn how to do here. So the first thing we need to do is to collect some data. So here's an example of a reaction where we're decomposing N2O5 in solution to NO2 and O2 at 45 degrees Celsius. We have our initial concentration of N2O5 is 1 mole per liter at time 0, and then about every 200 seconds or so we take the concentration of N2O5. Now it should be interesting to note here that determining concentrations of reactants in a reaction like this, a little tricky. You don't have a probe in there that sort of measures concentration. You'd actually have to quench the reaction. You have to stop it, or take a sample and titrate it, for example, to figure out the concentration. But as you're doing that, you're changing the concentration of reactants left, and that causes all sorts of problems. So the actual work going into create this data is fairly extensive. We're not going to worry too much about that. We're going to worry about what do we do with the data now that we have it. We can graph concentration of N2O5 with respect to time. We get a nice curve. We can determine instantaneous rates by finding the tangent line and finding the slope at any particular time. What we then get is a set of data that we can use to determine our form of our rate law. So this is still the method of initial rates, and it's used to find the form of the rate law. We're going to choose a reactant to begin with. We find two experiments. We have to run this reaction several times with different concentrations to try to figure out what happens to the rate as concentration of different reactants change. So we're going to have several runs of this reaction. We're going to try to find two experiments where the concentration of that reactant, the one that we're interested in, changes, but the reactants stay exactly, the other reactants' concentrations stay exactly the same. And then we're going to write the rate laws for both experiments. We're going to divide one by the other, and we're going to use log rules to solve for the order. Now it sounds fairly complex. It's actually pretty easy, and in a lot of cases you'll actually be able to do it in your head without actually doing the equations out. But I'm going to show you how you do the math, and then I'll show you how you do it in your head in case you have that option. And then once you found the rate of, or the order of one reactant, you do the same method to find the order of the other reactants. Okay, so here's some rate data that was taken from those graphs we just saw a second ago. The initial rates from 3 experiments for the reaction of ammonium ion plus nitrite ion to form nitrogen gas and water. Okay, we have 3 experiments. The initial concentration of ammonium ion was 0.1 molar in the first 2 experiments, and then it was doubled in the third one. The initial concentration of NO2 was 0.0050 molar, then it was doubled for the last 2 to 0.01 molar. And the rate was measured at various times. Okay, so this data we're going to use for the next couple of calculations. So you may want to stop the video here and just quickly jot down this little table, or open up your book to table 12.4 and follow along with the data. Okay, so we're going to choose one reactant to start with. Let's say NH4+. We're going to figure out the order of NH4+. How does the concentration changing in NH4+ affect the rate? All right, so we find 2 experiments where the concentration of that reactant changes, but the other reactants stay the same. Well, there's only 2 reactants, NH4+ and NO2-. And if we look at this carefully, NH4+ changes between experiments 2 and 3. It doubles. But the concentration of NO2 doesn't change between experiments 2 and 3. So let's use experiments 2 and 3. Okay? We're going to write the rate law for both of those experiments. Experiment rate for rate 2, rate is equal to 2.70 times 10 to the minus 7th. That's the rate. And from the table is equal to k, the constant, which we don't know, times 0.100 to the x power, we don't know what x is, and 0.010 to the y, the concentration of NH4+ and the concentration of NO2-, raised to their powers. Okay, the rate law for the second experiment, experiment 3, is the rate is 5.40 times 10 to the minus 7th is equal to k times concentration of NH4 to some power times concentration of NO2- to some power. And so I fill in as much information as I have from the data. Okay. Now the nice thing is that I can cancel out a few terms that are exactly the same. K is constant, both in the top equation and the second equation, and 0.010 to the raised to the y power is the same in both the top and the bottom. So I can actually cancel those out. What I then do is divide what's left, divide the two rates, and divide 0.100 to the x by 0.200 to the x. If you use your algebra, you will realize that 2.70 times 10 to the minus 7th divided by 5.40 times 10 to the minus 7th, that's 0.50. And then 1/2 to the x, or 0.50 to the x. And then we use log rules, the anti-log of both sides, and we get x is equal to number 1, x is equal to 1. So the order for NH4 plus is 1. It's first order in NH4 plus. Okay, we can do the same thing for NO2. We can use experiments 1 and 2, where the concentration of NO2 changes, but NH4 stays the same. We can do the same sort of setup, and we find that y is equal to 1. And so our rate law is now rate is equal to K times concentration of NH4 plus to the first power times NO2 minus to the first power. The overall reaction order is the sum of those exponents, so it's second order overall. Okay? Go back and take a look at it if that was a little confusing and see if you can follow along. Right? Now we can use the values from any experiment. Once we have the rate law, we can use the value from the experiment to calculate K. So it doesn't matter. All I needed to know was those exponents. They were both 1s. So I can take any experiment and I can plug in the value for the rate, the value for the concentration of NH4 plus, and the value for the concentration of NO2 minus. This is the first equation, or the first row of data. And I can solve for K. And so in this case, K is 2.7 times 10 to the minus 4th liters per mole per second, or mole seconds. That is K for all of these reactions. It's constant. The units of K tell me something about the reaction order as well, but we'll get to that later. Okay, the order of reactants will change the units of K, and that's, you can sort of see what's going to cancel and what's not. So let's take a look at another reaction, some more data, and we'll take a look at how we can do this. Sometimes you can just do it in your head if you kind of have the basic idea down. Right? So we need to find the orders of all three reactants. And we'll start with the BrO3 minus, that's called bromate. Okay? I want to find two reactions where the concentration of bromate changes, but the other concentrations stay the same. If you look at equations 1 and 2, the concentration of bromate doubles, the other concentrations don't change, so they're not going to affect the rate in this case between these two, but the doubling of the bromate concentration changes the rate. How does it change the rate? Well, it goes from 8.0 times 10 to the minus 4 to 1.6 times 10 to the minus 3. The rate doubles. Between experiments 1 and 2, the rate doubles, and the only thing I changed in concentration of reactants was I doubled the concentration of bromate. That means that it must be first order in BrO3 minus, because remember, when you first order in a reactant, you double the reactant, you double the rate. That's exactly what's happening here. If you want to do it by the calculation that I just showed you, this is what it would look like. Okay, you take the two rate laws, you plug in, you cancel out like terms, you do the division, and you solve for the exponent that's left there, x. Okay. Well, what about Br minus? So let's find two reactions where Br minus changes, but the other ones don't change. If you look at numbers 2 and 3, the concentration of bromate stays at 0.2, the concentration of H plus stays at 0.1, but the concentration of bromide, Br minus, doubles. What happens to the rate? 1.6 times 10 to the minus 3 to 3.2 times 10 to the minus 3. The rate also doubles. So doubling the concentration of bromide, Br minus, and not changing anything else causes the rate to double. That means bromide is first order as well. And there's the calculation to prove it. Got one more reactant to go, H plus. So let's find two equations where the concentration of H plus changes, but the others don't. How about 1 and 4? Concentrations of bromate stays at 0.1 between 1 and 4. Same thing with Br minus, but H plus doubles from 0.1 to 0.2. What happens to the rate from experiments 1 and 4? 8.0 times 10 to the minus 4th, 3.2 times 10 to the minus 3rd, that's 4 times faster. So we doubled H plus, the rate quadrupled, that means it's second order in H plus. There's the calculation to prove it. So our overall rate was first order in bromate, first order in bromide, and second order in H plus. Our overall rate law should be K, constant, times BrO3 minus to the first power times Br minus to the first power times H plus to the second power. The overall order of the reaction is the sum of those exponents, that's 4. And we can solve for K by plugging in any one of those lines, any one of those experimental data lines, plug in the values into the rate law that we just figured out, and solve for K. So I use the values from the first one. They're all concentrations of 0.1, and the rate is 8.0 times 10 to the minus 4th. We get 8.0 liters cubed over moles cubed times seconds. That's the unit for a fourth order reaction. That's what the unit of K is. You don't really have to worry about the units of K, but you do have to make sure that they're correct. You don't have to worry about what they mean, but you do have to make sure that they're actually correct. And that's done by just canceling out your units and setting up the equation correctly, as I've shown here. Okay? So there's a lot to do here, but a lot of times you'll just be able to look at a set of data and do it by looking. If you look at a set of data and you can't find two equations or two sets of data where the reactant that you're interested in is the only one that changes, well, then you have to do it by the equation method, by the calculation method that I showed. Okay? It takes a little bit of practice, but there's some problems at the end of the chapter. Lots of these where you can use the method of initial rates to figure out the rate law and then the value of K. We'll do a couple in class as well in your practice.